Okay, physics time. So physics is full of surprising connections, and today I'm going to tell you about one such connection that's relevant to my research in quantum physics. So I'm Alex from Ben-Gurion University, all the way from the desert of Beersheba, and indeed I'm going to tell you what links a forest fire to a coffee machine. So I'm going to start with a simple question. How could we model a forest fire? So one such way that I'm going to propose is we start with a grid. And I'll apologize, after the last presentation, my graphics are a bit more rudimentary, as you will very shortly see. So we can start with a grid, and this is going to be where we plant our forest, say. And we're going to fill it full of trees, beautiful hand-drawn trees. And importantly, we're going to do this randomly. So in each square here, I've put a tree with a probability of 0.44, so 44%. And we've done so randomly throughout this whole grid. And the question I have here is, if I start a fire in my forest, is it going to spread? Is it going to burn down the whole forest, or is it going to be relatively localized where we started it? So if we take, so here we go, start a fire, want to know if it spreads. And if we take a low probability, so I haven't got very many trees, you can see the fire is not really going to spread. The trees are in these isolated clusters, the forest is not really connected together, so the whole thing's not going to burn down. If, on the other hand, we have a very high value of P, we have loads of trees everywhere, almost all of them are in one big cluster, so when I make a little fire at the bottom, the whole forest is going to burn down very bad. So it stands to reason, if when P is very high, everything burns down, when P is very low, only a few trees burn down, there must be a crossover point. And more specifically, the question we'll ask is there a point where the fire first reaches the other side of the forest? So we can use this as our criteria for, does the forest burn down? We'll ask, does it reach the other side? And indeed there is, and we call this the critical value of P, or PC, and in this case, it's 0.44. But you might think, why is Alex talking about trees and forests? Why am I talking about all this stuff? Well, it turns out that what I've just described to you in the language of trees and forests and probabilities is something called percolation. It's exactly percolation. And percolation takes its name not really from forest fires, but from the physical percolation of a fluid through some sort of porous material. So if you listened to Rolando's presentation earlier, you would have heard about the movement of, say, CO2 throughout porous rocks, and it's exactly in this sort of physical scenario that people first started looking at percolation. And so this is where we make the link to the coffee machine, right? A percolating coffee machine, because I can use exactly the same model, instead of modeling a forest fire, to model the movement of water through a bed, say, of coffee grounds. So in this second beautiful graphic, I've got some little coffee beans representing my coffee, and here it looks like we're at some sort of critical value where the water is only just making its way from bottom to top. Another question you might have is, well, I thought you said you did quantum physics, Alex. What's this percolation got to do with physics? Well, I do physics, and what I study is a type of percolation that I'll describe to you, but first we have to set it up a little bit. So I make use of a map from interacting quantum particles, which I've represented by this sketch on the left. It's not a realistic sketch, but it will do. Interacting quantum particles to graphs. Now the important thing is each configuration of these particles can be represented by a node in our graph, so this little circle. So this is one configuration, it maps to a node. I might have another configuration, this adds a second node to our graph. A third configuration adds a third node, and so on until we build up a whole graph representation of our interacting system. So to make it really clear, each circle on the right here represents a particular configuration of my particles, and the links drawn between them, I draw a link whenever I can go from one configuration of particles to the other, according to whatever the rules of the system I have are. Now what I do is I take these quantum systems and I apply constraints. And I mean that in the literal word of the, meaning of the word constraint. I will restrict the movement, I will constrain the movement of the particles in some fashion. And the effect this has is to disallow some of those transitions between configurations. And that breaks links on the graph. So you can probably already see how this is looking a bit like percolation, right? So now I've got this graph, I've applied a constraint, and I've fractured it in some way. So analogously to varying the value of p we had earlier with our forest, I can vary how many constraints, how strict the constraints are that I apply to my system. So if I apply only a few constraints, I disallow only a few of those transitions, my graph is pretty much intact. But if I heavily constrain the system, I fracture the graph into small clusters again. So before we had little clusters of trees next to each other, now we have clusters of nodes that are linked together. And so there must therefore be some crossover point. There must be a critical sort of strength of constraint at which the graph is sort of only just held together. Constrain it anymore, it will fracture. So this is what I do. I try to figure out for some quantum systems how the constraints on those systems relate to this sort of percolation property of whether or not the graph is held together. The reason I do that is because there's a direct analogy between earlier we were looking at does the fire spread through the forest? Here I have can quantum information move through my system? So if I have only few constraints, there's the free flow of quantum information. If I have many constraints, there's no flow whatsoever, and I'm trying to find out, well, where is that crossover point? Now, this is blue skies research, and to be honest, I do this because it's quite fun. It doesn't have any immediate applications, but people are interested in these sorts of problems and in the movement of quantum information in particular to try and plan useful materials and devices for quantum technologies of tomorrow, maybe I'd say in a grant application. But I want to leave you with one thing. So we've looked at this process of percolation, and we've seen that it can be applied to modeling forest fires. I mentioned it could be applied to modeling, say porous rocks, through physical percolation, the coffee machine, and now this quantum system as well. And this fact, this sort of feature of physics where the same physics can guide many different physical processes, has a name, and it's called universality. So with that, I invite you to please ask some questions.
So my name is Max from Tel Aviv University. As a short disclaimer, I don't know anything about quantum physics, so there's a high risk that my question is actually a dumb one. If you constrain the system in a way, does it become more efficient when you do quantum computation? Like, is a more heavily constrained system more efficient? Like, can you speed up certain computational processes if you constrain a system right to the point where it still works, where you still have all the links, but not too many links?
So as far as I understand, and I'm not an experimentalist, so please don't ask me how one actually does this in the lab, but as far as I understand, people are interested in these sorts of questions not so much for sort of efficiency reasons, but rather for things like, how do I store information? So you can imagine if I have a system where there's no free flow of information, where if I excite some particles or something, then the knowledge of that happening doesn't spread throughout the system. That can be used as some sort of storage device. So I think this is the sort of rough outline that people have, but yeah, ask an experimentalist how in practice it works.
Cool, thank you.
Thank you. My name is Ronan Gottesman from the Hebrew University, and I don't understand anything about quantum physics, so maybe my question also is kind of stupid. But while you were giving your talk, you mentioned Blue Skies research, and I looked at it on Google, and it's very interesting. Basically, it says that it is used interchangeably with the term basic research, which is also very important. But my question, can't you think about any application like quantum computers that you can use your research to correlate with or help?
Yeah, so I guess kind of the aim of a lot of, so this is, I guess, would fall under the umbrella of theoretical condensed matter physics. So a lot of condensed matter physics is sort of very immediately useful. And then there are, research projects such as this that are more on the abstract side, that it's not quite obvious where we would use it now. But I guess what one hopes, right, is that it's part of some broader understanding of how things like, the movement of quantum information works. And that hopefully in the future, when that's all been settled and people understand these complicated interacting systems to a greater degree, then they can start trying to use these to make actual technologies. So this is how I'd phrase it.
Thank you.
So is this working? Yeah. Tom from the University. Fascinating. Questions. Do you also study beyond the phase transition probability, or you call it the crossover? Do you also study different properties of different configurations that are all strongly connected? So, you can get different, like in the forest fire example, you get many different configurations with a whole forest will burn, but in some configurations it will take longer for the fire, right? So like the average path length and stuff like that. So do you also study that in your work?
Yeah, I mean, you hit on something very crucial, is so we can look at this transition precisely by asking kind of how long does it take to get from one side to the other. So we're on one side of the phase transition at low p, that time is infinite, it will never reach the other side. And I can diagnose where this transition is, essentially by plotting how long does it take to get to the other side. And you see a discontinuity there. So, 0 on one side. If I started on the other side, deep into this, the region where everything is one cluster, that time will be very short. But as I approach the transition, it will diverge. So that time will get longer and longer. And exactly at the transition, you get these strange sort of fractal paths where, the fire does eventually reach the other side, but it does so by going a long, circuitous route. So we do look at that. And the second thing I'd add is an important part of, the universality, say, of percolation is that, the phases are very well understood and the minor details don't matter that much. So, the physics of being in a percolating or a non-percolating phase is kind of a universal property. So we spend less time focusing on those because it's, the behavior is more well known. The interesting stuff happens around the transition.
And do you have analytical kind of expressions for this, or is it all simulation based?
So there are some esoteric mathematical works on these graphs because these graphs have very high dimensions, right? And in the simplest cases, you can solve them. So for the graph that is just a hypercube, that was solved some time ago. And I look at the paper, I don't understand the mathematics. It's very, very difficult. But in most cases, analytics are useful, but you probably wouldn't hope to be able to, say, find the location of the transition using mathematics alone. At least I wouldn't.
Kasia from Technion. Thank you for a great talk. I have a question. As far as I know, in quantum mechanics, it works like that when you observe your results, the states could change, like famous Schrödinger cat example. And in your research, did you check different constraints on the same system and how this affect your results?
Yeah, sure. So as far as the kind of, observing things, I guess the technical detail is that you'd have, some interacting quantum system and you map it onto a single particle problem on this lattice. So we're looking at, it's a simpler problem because you have one sort of fake particle moving on this high dimensional graph, but of course your graph is much more complicated. And so we do look at the eigenstates on the graph as well of that single particle system, and there of course you run into everything where, if I make a measurement, I'll collapse it and so on. But that's not so relevant. We're more interested in the eigenstate structure. And as for the second thing, doing different types of constraints, yeah, absolutely. We do lots of different things, and one of the kind of research aims is almost coming up with interesting constraints. I mean, I can go into more detail. Probably the very technical details are kind of boring, so we can talk about it afterwards.
Thank you. I would love.
Great talk. Thank you very much.
Thank you.